Fluid. A fluid is a substance that can flow. A fluid is a substance that cannot maintain its own shape. Alright. So if it cannot maintain its own shape, what kinds of stuff are fluids?
Liquids.
Liquids? What else doesn't maintain its shape?
Gases.
Liquids and gases are fluids because neither have an orderly arrangement. So liquids often are referred to as being incompressible. If they are compressible, they are not very much compressible. Whereas we know gases, we can compress them as much as we push on them, and as long as they don't turn into liquid. Okay. Density. Density is defined as the mass per unit of volume. So the units are going to be kilograms, mass units, over meters cubed. Or we could have grams over centimeters squared, centimeters cubed, sorry. And we know this because our density formula, we used to say density is a broken heart, mass over volume. And so you can sort of see the heart shape right there. As far as these two density units go, there are 1,000 grams in a kilogram. And there's 100 centimeters per meter, but it's cubed, right? So actually the smaller unit is grams per centimeter cubed. Or, sorry, I think the more dense unit is actually grams per centimeter cubed. Right? It should be...
Grams per centimeter cubed will have a larger value than kilograms per centimeter cubed.
Yeah, 1 gram per centimeter cubed should be 1,000 kilograms per meters cubed. Because here's what this is. A kilogram per meter cubed is going to be 1 meter stick by 1 meter stick by another meter stick. And so it's like the size of a small hot tub, really, when you think about it, because a meter deep is pretty deep. And a meter in both width and length is pretty deep, right? It's like 3 feet by 3 feet by 3 feet almost, because a meter is about a yard. So the density of water, this Greek letter is rho. So this thing that I'm kind of drawing, I'm going to try to make it curvy to begin with, and then I'm going to make it curvy up top. That's going to be rho. Yeah. And so the rho, or the density of water, has a maximum density of about 1,000 kilograms per meters cubed at 4 degrees Celsius. That's about as heavy as water gets when it's at 4 degrees Celsius. That unit-wise is 1 gram per centimeter cubed. So we start to see that 1 gram per centimeter cubed is actually like 1,000 of these. That's how much bigger this is. Ice, however, is heavier or lighter?
Lighter.
It's lighter. Or, sorry, it's less dense is what we should say. And so 917 pure ice would be about 917 as a solid, or 0.917 grams per every centimeter cubed. So about how much of an iceberg would we see above water?
92%.
About 92%, but then again, it's also salt water. So it would float a little bit more of the iceberg as well. And unless specified, we have the density of air. The density of air is about 1. I should use the squiggly lines for about 1 kilogram per meter cubed. So which one's lighter, air or ice?
Air.
Obviously, right? Like we throw out ice into the grass and the ice doesn't float up to the sky. We're good. Not crazy. All right. The next topic we have to talk about is called specific gravity. Specific gravity. Okay. So specific gravity is equal to the density of a substance divided by the density of water. It's just a ratio of densities. So what happens to the unit?
Cancels.
Okay. If the units cancel, it is unitless. If we have, so here's some sample problems of everything we've learned. We're going to use specific gravity, but we're also going to use the density formula. Right here they give us 10 to the negative 3 meters cubed. That's 0.001 meters cubed of oil. But how big is that? What would you call that? What would the normal person call that in, I guess not here, but in maybe Europe? It's 1 liter. A liter of oil has a mass of 0.8 kilograms. What is the density? Oh, this is easy. So we're looking for the density, and we know that it's mass over volume. So it's just 0.8 divided by 0.001. 1, 2, 3. 1, 2, 3. I got 800 over 1. Or just 800. 800 what? What's the unit for this?
Kilograms per meters cubed.
And the units are the most important part. Kilograms per meters cubed. Good. Because honestly, the math for this isn't hard. The conversions and keeping track of your units and making sure that everything lines up, that tends to be the hardest part right now. Turpentine has a specific gravity of 0.9. That's unitless, so that's specific gravity. What is the density? So our formula for this is specific gravity equals the density of the substance, that's what we're looking for, over the density of water so we have 0.9 equals what we're looking for over what? Over 1,000 kilograms per meters cubed. We could just cross multiply and we get that the density of the substance is equal to 900. And of course, the top unit is decided by, or our answer units is decided by,
The density of water.
yeah, whatever units we use for our density of water. So if we use 1 gram per centimeter cubed for the density of water, we could just say it's 0.9 grams per centimeter cubed. All right, pressure. The reason why density is rho is because P,
Pressure.
I was going to say is momentum. We've got to be very careful. I'm going to skip back to before. That when we're talking about rho equals m over v, that's rho or
Give Devin his pencil back. Give Devin his pencil back. Well,
that rho equals m over v. That's, what did we say? This is density is equal to mass over volume. We want to make sure that we don't mix that up with P. Momentum
which is mass
is
times
mass times, not volume, but velocity.
That's why you want
mass times volume.
Yeah, that's right, bro. You don't have your hands for the heat. That's why you have to remind yourself.
All right.
You know, it's
So density is actually not the letter P, but the Greek letter rho. Now over here, we've got another P. Pressure P
Yeah, $2.
is defined as the ratio of a force spread across an
Go get it back.
area
Give me 20. Go get it back.
or acting perpendicular to that area is the way it's textbook written. This force is the pushing force. It is never, pressure is never a pull force. Okay.
That is definitely going to be on the test.
So P, pressure, is force over area. You've seen this. How do we measure our tires? What kind of unit? PSI. What does that stand
Pounds
for?
per square inch.
Pounds per square inch. Okay. So our PSI. That's PSI, pounds per square inch. That's so
American.
American. Is a vector force that crosses the area or pushes on an area. Okay, so they're both vectors. Yes, area is a 2D vector. Okay.
Oh, it's 2-dimensional.
Units are Pascal, or we also have in SI world newtons per meter squared. Just like we had pounds per square inch, we have newtons per meter squared. Pounds per square inch is a big unit comparatively. A pound is, there's 2.2 of these per every kilogram. So that's not the big part of it. Well, it is a little bit bigger than a newton. Because there's 10 newtons in a kilogram. Or 9.8 newtons per kilogram, typically. Pounds versus newtons. Also, though, the per inches squared, a square inch. I could draw a square inch on this piece of paper. Okay, that's about a square inch for me. I guess it's different up here, right? It's different on the screen, but on the paper, that's about an inch for me. Okay, what's a meter, though? A square meter would be that big, okay? So it's a very small force exerted on a very large area. That's not much pressure at all, okay? So pascals are actually oftentimes not just pascals, but we'll see prefixes to it as well, like kilopascals. Okay, 1 Pascal is the pressure when a force of 1 Newton acts perpendicularly on a surface of 1 meter squared. So 1 Pascal is 1 Newton per meter squared. Pressure is a scalar quantity. However, these two have arrows on it. Force is a vector. And area is a vector. Oh, yeah.
Vector. Yeah.
And the average atmospheric pressure at sea level, we know, is 760 millimeters of mercury. You might have used that in chem class. You would have definitely used it maybe in chem 2. Us Americans, yes, we do divide that by 2.56, and we talk about inches. Sorry, well, that would be centimeters of mercury.
760 millimeters of mercury is 29.92 inches. Of
Yeah,
mercury.
we would convert it into inches. But
We use inches in aviation.
for us, it's easiest to think about, and a lot of the way we think about it is 1 atmosphere. So the units of pressure at sea level, equatorial sea level, is 1 atmosphere, which is 760 millimeters of mercury. And for us, that's 101.3 kilopascals, which is 101,300 regular pascals. Huh?
13.
We said that pascals was a very small amount. Therefore, a lot of times we see it in kilopascals. The tool to use to measure atmospheric pressure is a barometer. Now, the big question is, though, how does a straw work?
Capillary action.
So how does a straw work? What's going on with a straw?